Ma'am, it is done.
Okay, thank you, ma'am. Okay, thank you, ma'am. We hope you are all finding great value and inspiration in today's insightful sessions and are all fully engaged in this AICT ATAL Faculty Development Program. So let's proceed to session 8, where we will explore the exciting topic of signal processing for millimeter wave hybrid MIMO systems. And also, dear participants, please note that you may share questions in the chat box and we will discuss them towards the end. So over to you, sir.
Also, kindly fill your feedback form on time so that you will get attendance for that also. And
Okay, thank you, ma'am. So I'm just sharing my slides. Uh, yeah. Is it visual, ma'am?
Yes, sir. Yes, sir.
Yeah,
yes,
thank you.
sir.
Thanks. Okay. So, yeah, welcome again. And yeah, in the second and final session, that is corresponding to signal processing for millimeter wave hybrid MIMO systems. So in previous session, I have gone for sub-6 for XL MIMO terahertz system, sub-terahertz system, but here I will go deep into the millimeter wave hybrid MIMO system. So all the basics corresponding to the MIMO is already discussed in previous session. So here is the next MIMO, that is a hybrid MIMO, and that is integrated with the millimeter wave, and how the signal processing can be performed for this integrated system is the basic theme for the presentation. So in this session, the content for presentation is corresponding to the different algorithms for channel estimation for the millimeter wave hybrid MIMO, and channel estimation for millimeter wave hybrid MIMO with hardware impairments, and next is channel estimation corresponding to IRS assisted millimeter wave hybrid MIMO. IRS means intelligent reflecting surface assisted millimeter wave hybrid MIMO system. So for these systems, I will go the system architecture, channel model for different systems, and then problem formulation, and after that proposed algorithm, and then simulation results will be discussed. So again, as we know that in previous session, I have also talked about the data rate from 1G to 6G. So the data rate is a basic binding force that for research is required, that how this can be increased, and the basic things is that corresponding to the applying different types of MIMO and different wider spectrums. So the KPI for 5G is that is a data rate, connectivity, latency. There are different numbers that I have already discussed. So to find the KPI for 5G and beyond, we have to go for a different spectrum as well as a different type of MIMO. So and the signal processing is basically either related to the channel estimation or beamforming. So here is the basically I have discussed about the channel estimation for the different millimeter wave related systems. So as I have already talked about that channel estimation is important for optimal beamforming or beamforming matrices that maximize the received signal power and mitigate the interference. And channel estimation also helps to characterize the propagation environment and adapt the transmission parameters. And it is necessary for spatial channel characteristics that enable spatial multiplexing, ensuring the transmitted signal. So the channel estimation is critical for any system, and it is also extremely important for millimeter wave communication. So basically, I have discussed all the fundamentals behind how the beamforming is possible for using multi-antenna system, and I have also gone for XL MIMO in previous session. So here millimeter wave MIMO, that is first of all the basic the critical term is related to hybrid MIMO, and then as we know that millimeter wave is a spectrum that is corresponding to 30 gigahertz to 300 gigahertz, and this is the system model for millimeter wave hybrid MIMO. The term hybrid here means to accommodate both or to cascade both analog as well as a digital precoder and analog and digital combiner at the receiver. Means hybrid mean we are applying basically two structure in the system that is corresponding to analog analog precoder, means RF precoder, and digital precoder at the transmitter side, and RF combiner and baseband combiner at the receiver side. So the basic difference between simple MIMO and millimeter wave hybrid MIMO is that in simple MIMO there is only analog architecture or digital architecture, but here if we use analog precoder only, then there will be many number of RF chain. RF chain means that accommodate that is basically a combination of power amplifier, filters, and digital to analog converter, ADC, and different circuit components that are here that connect the antenna system. So when we increase the number of antenna, then basically there will be as many number of RF chains, as many number of antenna if we use only digital precoder. So due to that, the complexity of the system increases, and also power consumption also increases, because in millimeter wave there are many number of antenna, means large number of antenna at the transmitter and receiver side. So there are many digital to analog converters or analog to digital converters, so corresponding to each antenna, and these are power consuming device. So if we make more in number of RF chains, then it will take large number of power. So we go for hybrid mode. Means in hybrid mode, the number of RF chains is less than the number of antenna basically. So it provide multiplexing gain, means in form of number of RF chains, and also we can find the beamforming gain from the number of antennas. So by this, by use of hybrid precoder and combiner, we can find two types of gain simultaneously, and that is a multiplexing gain as well as a beamforming gain. So this is a basic reason that why we go for the hybrid MIMO transceiver for millimeter wave system. So the basic reason is to reduce the complexity, reduce the power consumption, and reduce the cost of the system. So this is the, here we have considered the single carrier narrowband millimeter wave hybrid MIMO system. Suppose there are NT number of transmit antenna and NR number of receive antenna, and NRF is the number of RF chain at the transmitter and receiver side. Both here I have considered same number of RF chains at the transmitter and receiver side. We can also change it, but for simpler region, means the circuit should be simpler one, so I have taken the same number of RF chains. And suppose there are ns number of parallel data streams that we have to transmit, and this follow the structure ns must be always less than the number of RF chains, and that must be less than number of transmit and receive antenna. So here here that is FBB is corresponding to a baseband precoder. Baseband precoder basically provide a multiplexing gain, and it also overcome the interference between different signals. And here is the RF precoder that provide the beamforming gain. So spatial multiplexing is done with the help of baseband precoder, and beamforming is basically here RF is basically steer the beams towards the receiver side. So FRF, that is RF precoder matrix, FBB, that is a baseband precoder matrix, and here WRF, that is a RF combiner matrix, and WBB, that is a baseband combiner matrix. And here are RF chains that I have already told, that RF chains means that is a combination of low noise amplifier and filters and ADC DAC converters and other circuit elements, that is known as RF chains, radio frequency chain. So here the order of FBB is corresponding to NRF by NS. Here we can see it is a order of NRF by NS, FBB, and FRF, that is corresponding to order of NT by NRF. And same we can find the WRF, that is NR by NRF, and WBB, that is NRF by NS. So, and here that we assume that the precoder and combiner matrices constitute of digitally controlled phase shifters. And basically RF beamformer that steer the signal to maximize the SNR at the receiver. So as in previous session, as I have told that for near field region, that for XL MIMO there is a near field region, that channel is corresponding in near field region, means where the wavefronts are spherical, but here for MIMO hybrid, for millimeter wave hybrid MIMO system, we have taken far field region. Far field region means we have taken the planar wavefront for that, and the channel for this system is given by the equation 1, where NT and NR is corresponding number of transmit antenna, NR is number of receive antenna at the receiver, alpha L, that is a Rayleigh distributed path gain of LF path, and AR, that is array response vector at the receiver, and AT, that is a array response vector at the transmitter side. Here we have considered the uniform linear array antenna, and the antenna and the response vector for that is given by this equation, which follow the Vandermonde structure. And here the D is the antenna spacing, means the distance between two consecutive antenna, and the lambda is the signal wavelength. So this channel model, that is geometric channel model, that can be represented in beam space domain by the equation 3, where AR is the transmit array response dictionary matrix, and AT, that is the transmit array response dictionary matrix, and AR is the receive array response dictionary matrix, and that is formed with the help of array response vectors at transmitter side and array response vector at the receiver side. And HA, that have a path gain that follow the Rayleigh path gain, and given by equation 4. So suppose we have suppose I have taken a pilot matrix of size identity pilot matrix of size NT beam, then the output signal can be given with the help of 7. Here you can you can see that here is the channel between a transmitter and receiver is H, capital H, and here Y, that is a received signal at this point, received signal at the output of the baseband combiner. Then Y will be the combination of these matrices into H into these matrices, and then the input signal, that pilot signal. So here the equation, that is a 7, in the same way we can write the equation, that is WBB, that is a baseband combiner matrix, WRF, that is a RF combiner matrix, and H, that is the channel between transmitter and receiver, FRF, that is RF precoder at the transmitter side, and FBB, that is baseband precoder at the transmitter side. So because we have to find the channel H with the help of these dictionaries, and means with the help of pilot signal and received pilot signal and transmit pilot signal. So it must be vectorized because it is in matrix form. So it must be vectorized. So the Y in vector form means vector of Y is given by, suppose, equation 8, where Q, that is given by the Kronecker product of combiner and precoder matrices, and transmit and receive array response matrices. Basically, if there are three matrices A, B, C, and if you want to vectorize, then there is a identity that vectorization of A, B, C is given by C transpose Kronecker of A vectorization of B. On the basis of this formula, this is the basically conversion form, and here Q is given by this formula. So here for estimation purpose, I have taken the FRF and WRF as a DFT matrix because it have a unit magnitude and different phases. So it excites all angular mode, but unit magnitude. And FBB and WBB, that are block diagonal matrices. So basically, HA for millimeter wave, that is problem formulation is given by this equation 9, where HA is basically the channel that is a vectorized form of beam space channel, that is here HA, small ha, that is a vectorization of this HA, and it is also sparse. So we have to find this the solution for this optimization problem. And again, there are many algorithms, but here I have applied the zero tracking LMS based algorithm. And like previously, here the basic thing is to apply this algorithm is to find the lower find the lower NMSE floor as well as lower computational complexity and improve the spectral efficiency. So here we have applied L0 norm penalty function, and on the basis of that, here I have find the gradient descent, and on that the update equation that is given by equation 17. After because as we know that L0 norm is non-convex, and to make the problem convex, here I have taken a suitable approximation that L0 norm is given by this formula, and after the approximation, we can easily apply the gradient term, and on the basis of that we can find the update equation. After finding the update equation, here is a pseudocode for ZLMS algorithm. Means first we take the initialization part and then find the error. After that, update equation, that is with the help of this one, and then find the estimated channel, overall estimated channel by this equation. And as we know that the spectral efficiency, that is same as I have told previously, that it is basically log 1 plus SNR, because it is in MIMO case there is a determinant of log 2 1 plus SNR. So here is the identity matrix plus to find the SNR. Here we have to multiply all these matrices, and then we can see that here F, overall F means F, the multiplication of FRF and FBB, and W, that is multiplication of WRF and WBB, are precoder and overall precoder and combiner matrix, and that are designed basically with the help of singular value decomposition of the estimated channel. So this is the basic reason why we go for the channel estimation for such a system, because if we want to design the optimal precoder and combiner, we require the singular value decomposition of channel H, and that we can estimate. So the spectral efficiency basically depend upon the accuracy of the estimator. So means if the estimator will be more accurate, then it will provide more spectral efficiency for the overall system. And here are the simulation parameters for the above system that I have taken. Here we have considered only one transmitter and receiver with multiple antenna, and both have a 32 number of antenna, and I have considered number of RF chain 8, and spacing between antenna is lambda by 2, and here I have taken 32 quantized value for angle of arrival and angle of departure, and system is assumed to operate at 28 gigahertz and had a bandwidth of 100 megahertz. And here I have considered path loss exponent 3. So on the basis of that parameters, here is the simulation plot. So basically this is the blue size guy, that is plot is corresponding to the perfect channel, and here optimal means corresponding to Wiener filtering, and the green color, that is corresponding to ZLMS L1, and violet, that is LMS, and here pink color, that is corresponding to ZLMS L0 norm. So we can see that ZLMS L0 means if we take the penalty function L0 norm, then it will perform close to the optimal and perfect channel. Means it will provide more accurate channel as compared to the other model, other estimator. And this is because of reason, because this minimize the L0 norm. What here we can see in the problem formulation. Where is a problem formulation that I have already, yeah, this one, because basically L0 norm is minimized this function, because it is also given in the problem, and L1 norm is basically L0 norm is non-convex, so to make it again convex, we take the L1 norm. But L0 norm provide the sparsest solution, so it gives the lower NMSE flow as compared to the L1 norm and LMS. So that is the reason why ZLMS L0 gives the lower NMSE, lower mean square error as compared to the other algorithms. And on the basis of estimator, here is the spectral efficiency versus SNR plot. So from the plot, we can see that here it is the perfect CSI corresponding to the perfect CSI, means the spectral efficiency increases as SNR increases. So here the pink color, that is corresponding to the estimator of ZLMS L0. Because ZLMS L0 is more accurate, so the spectral efficiency corresponding to that estimator is more close to the perfect one and higher to the others guy. So this is the estimator for millimeter wave hybrid MIMO system. In the next work, I have gone for the estimator for the millimeter wave hybrid MIMO system with hardware impairment. Because the hardware impairment is basically occurs due to the power amplifiers and local oscillators, and this is a type of due to this hardware impairment, there is a distortion occurs at the transmitter, means there is a distortion in the pilot signal. So the channel estimation become problematic if we take if we does not take this distortion into the consideration. So here I have shown that how we can minimize the effect of a transmitter and a receiver distortions, means if we consider the hardware impairment, then how the these effect, how these distortion affect the overall system. So this is the basic generalized transmission with hardware impairments. Here D is the suppose intended data, means suppose it is a pilot, and eta T, that is a transmitter distortion, eta R, that is a receiver distortion, and N is the AWG noise. N is the basically here N noise is corresponding to thermal noise, and these are distortions are also noise that arises due to the IQ imbalance of local oscillator and saturation of power amplifiers and other circuitry. So these also have considered the Gaussian distribution in this consideration. So here, if we take the hardware impairment, then the received signal can be given by equation 22, where H, that is the overall channel between transmitter and receiver, D is either a deterministic pilot signal or stochastic zero mean data signal or information signal, and eta T, that is distortion at the transmitter. Here I have taken a Gaussian distribution for this, and eta R, that is receiver distortion, means the distortion at the receiver side. So, and because it is a complex normal distribution, so suppose here eta T has a zero mean with gamma T variance, and eta R, that has a zero mean with gamma R variance, and gamma T and gamma R variance can be given by these relations. Here gamma T is the product of KT diagonal KT, that is the proportionality coefficients, and KR is also proportionality coefficient. and C11, CN2 are the diagonal element of the signal covariance matrix, means that is the covariance matrix for D, means it is a, if we find the covariance of input signal, then it is given by this relation, and here the elements are that these are elements are diagonal elements of the signal. So the, because variance represent basically the power, so the power corresponding to the transmitter distortion is given by this variance, and gamma t, and power corresponding to the at the receiver side is given by. So here we can see that power depend on the receiver distortion noise has a power that depend upon the signal power, means trace of C, and because trace of C gives the signal power overall. So as the signal power increases, the receiver distortion increases. So here is the basically transmitter and receiver architecture for millimeter wave hybrid BIMO with hardware impairments, and these pink color shows the non-ideal hardwares, and basically it is, these are the RF chains that consist of low noise amplifier, mixer, and voltage gun, VGA, and analog to digital converter, automatic gain control. These are the part of this RF chain, and these, suppose these are non-ideal in that case, so they are basically producing the distortion of for the signal. So here for here again FBB, FRF are the baseband and RF recorders, and WRF, WBB are corresponding to RF and baseband combiners. And here receives signal at the receiver. This is the receiver part. Lower below is the receiver part, and is the transmitter part. So at the receiver there is received a signal that is given by this equation, where D is the intended signal, means either it may be the pilot or data signal. So after applying the identity matrix for a pilot, the received overall received signal matrix that can be given by equation 33, where n is the overall AWG noise matrix, and eta t and eta r are, as I have explained earlier, that are the distortion at the transmitter and receiver side. And here again FRF and WRF that have taken the DFT matrices, and FBB and WBB are here I have considered the block diagonal matrices. So again, after for estimation purpose, we have to again vectorize that equation, and after vectorization we can find the vectorized form of received signal y, that is given by equation 24, where q that is given by this relation, that is again Kronecker product for the different matrices, and here n tilde, that is a vectorization of basically it has two noise, means the receiver distortion noise multiplied with overall combiner matrix, and thermal noise, thermal AWGN noise, that is n, and that is given by product of WHN. So after vectorize the equation, again we find the cost function, and after finding the cost function, here different algorithm I have applied, that is variable step size least mean square algorithm, and after applying this algorithm, previously I have applied fixed step size zero tractor LMS. Here I have applied the variable step size, and that is the basic framework for VSSZ LMS. Here is the basic estimation problem, that again we have to minimize the L0 norm of HB, means beam space domain channel, and then here is the VSSZ LMS cost function that is given by this, and here we can see that the basic difference between variable step size is that here is the step size is basically varying in each iteration, and that is given by this relation 27. So applying this algorithm, here is the basic pseudocode for that algorithm. We can find the estimated channel by this relation, and again spectral efficiency is given by this relation, and here eta, that is the overall noise of the system, is given by this, and the here that is covariance matrix for error, that is given by kappa t into P by NRF and kappa R into P, where P is the power of transmitted signal. Here, if we increase the power of transmitted signal, then we can see that kappa T and kappa R, suppose the constant, then this has a severe effect as compared to this part. So we can see this effect in simulation. So again, if the estimator will be more accurate, then spectral efficiency of the overall system will be high. And these are the system simulation parameters that I have taken, and for that again I have taken the transmit and receive antenna as 32, number of RF chain 8. Here the mu maximum, that is I have taken 0.03, and mu minimum means the minimum step size, that is a 0.1 of mu maximum, and accuracy of the parameter, that is 15, and path exponential factor, that is 3. So on the basis of that parameters, here the NMSC versus SNR plot. So we can see that as the SNR increases, the NMSC of all the algorithm NMSC of all the estimator decreases. Here is the corresponding orthogonal matching pursuit that has a higher NMSC floor as compared to the Bayesian compressive sensing, that is a BCS, and sparse Bayesian learning. So here the proposed one, that is a variable step size ZLMS L0 with kappa T and kappa R, means the proportionality factor is 0.1 square. Corresponding to that, here we can see that the proposed algorithm offer lower NMSC floor for same SNR as compared to the existing algorithms. So on the basis of that, here is the plot for spectral efficiency versus SNR. So there is, if we increase the SNR after a certain limit, then we find the floor corresponding to the different number of kappa value because of due to this factor, because of this power factor, because when we increase the power, then the effect of eta T and eta R increases, and due to that effect the overall spectral efficiency become constant. And we can also see that kappa T has lower impact as compared to the kappa R, because suppose here that is a violet signal for kappa T 0.15 square, kappa R 0 here, and here that is a green plot. Green plot is this one, and violet plot is this one. So here we can see that kappa R has more severe impact as compared to the means the receiver side distortion has more severe impact as compared to the transmission side distortion. So that is a basic finding of the this work. So in this work I have proposed estimator that is based on variable step size zero attractor algorithm, and that is applied by considering of system of millimeter wave hybrid MIMO system with hardware impairments. And in the next part, that is a combination of millimeter wave hybrid MIMO system with IRS assisted. Basically, what happens if suppose the direct line of sight between transmitter and receiver is blocked, then we apply the another mean that is known as intelligent reflecting surface to provide a virtual path between transmitter and receiver. So basically IRS, or intelligent reflecting surface, is a major key enabler for 5G and 6G, and it is used to provide virtual line of sight, or you can say that it is used to increase the communication range and accommodate more number of users. So it also increase the connectivity and coverage of the overall system. So here IRS structure is applied. Then so basically this is the combination of millimeter wave hybrid MIMO system assisted with IRS. So here is the channel between transmitter and IRS, HTI, and HIR is the channel between IRS and receiver, and IRS is modeled with theta here. And again, the millimeter wave has the same structure as corresponding to previous works. So the basic basic target to estimate this, the cascading channels, mean HTI, theta, HIR. So in this system model, here is the again this is the far field model, and here HTI is channel that is corresponding to between IRS and the transmitter side, and HIR is the channel between receiver and IRS, that is given by this relations, that is a geometric path model. And here we have considered downlink propagation scenario, and here AIRS is corresponding to the array steering vector corresponding to the IRS, and ABS is array steering vector corresponding to the base station, and AUE, that is array steering vector corresponding to the user. And NT is the number of transmit antenna, M that is a number of reflectors in the IRS, and eta and mu are different path loss component from between transmitter to IRS and IRS to the receiver. So here again HTI and HIR, that is given by this relation as in previous model. So here AIRS, that is corresponding to the response array response dictionary matrix of the IRS. ABS is the corresponding to the array response dictionary matrix at the base station, and AUE, that is the array response vector at the user. So these are formed with the array steering vectors, and AIRS, that is means array response dictionary vector at the IRS, that can be given by Kronecker product of AX and AY. AX, that is corresponding to the horizontal components, and AY, that is corresponding to Y coordinate system. So the vectorization of H can be given by this equation 36. So basically we have to not go into much detail into the mathematics part, but here we have to understand that how this IRS affect the overall channel. So the overall channel for this is basically cascading of HTI, HIR, and theta. Theta, that is the basically modeled by IRS, and theta, which have here theta is basically, that is a diagonal of theta. I have not written, I think. Theta is basically diagonal part of the reflector. Reflector have here I have taken passive reflector, means there is no amplitude change, only phase change. So that is model, the IRS model with this theta. So after finding the overall channel, this term can be simplified by the equation 38. And after finding this simplified form, the overall received signal vector Y, that is given by equation 39, where xi, that is given by this relation, and HB, that is a vectorization of this delta, and basically this delta is a matrix of means cascaded channel matrix. So again, after applying this cascading channel, we have to estimate the sparse vector HB, means cascaded part of all the channel, this HB, by knowing the Y and this psi. So here again the considered system model is given with the help of channel estimation problem, that is given by equation 40, and there are many algorithms, but I have here applied the recursive least square algorithm, and that is given by this equation 41, and here delta, that is a forgetting factor, and EL is given by this equation, and here H hat, that is a estimated part. So because RLS motivates the consideration of approximation in cost function with a shorter sliding window, means if we take this equation, then it is a very much complex in nature, because the size of here size of delta is quite large. So we form a window, and that is a slide in this fashion, and here W is, that is corresponding to sliding window length, and then apply this algorithm, we can find the weight update by the help of 43, where mu is the step size, and on the basis of this is the basically corresponding known as exponential forgetting window LMS algorithm. So here we have to find the delta, that is diagonal matrix, and that is corresponding to weighting factor delta this. So here delta is given by this equation, the equation 44, and R that is given by this one, and error means that is a vector of different slide corresponding to different sliding window, and here Dn is the desired signal, and H hat that is estimated one, and R and that is a sensing matrix. So on the basis of that, here zero attractor sparse solution for of the final gradient descent weight update is given by this equation 46. And after finding this update equation, we can here apply the sparse exponential forgetting window least mean square pseudocode for sparse exponential forgetting window least mean square algorithm. And on the basis of this algorithm, here are the simulation results that with the help of these parameters, I have find the simulation results, and it is the basically an MSE versus number of iterations plot, and the lower green part that is corresponding to Oracle least square. So for benchmarking purpose that I have taken and compared with the existing algorithms like sparse Bayesian learning and OMP algorithms. So here again we can say that SEFW LMS based algorithm, that is this one, is performing better as compared to the other existing algorithm. And here is the NMSE versus SNR plot. So here we can see that SEFW LMS, all the existing algorithm follow the same pattern, means if we increase the SNR, then the mean square error decreases, but the decreasing rate of SEFW means proposed algorithm has lower one as compared to the other existing algorithm and close to the benchmark, means it is the benchmark Oracle least square. So on the basis of that, here the spectral efficiency versus SNR is plotted. So we can see that more accurate estimator give higher spectral efficiency, and that is close to the Oracle least square, means that is a benchmark. So as SNR increases, the spectral efficiency of all algorithm increases, but the spectral efficiency of proposed one has higher value compared to the existing. So this is the in this work we have proposed a novel SEFW based algorithm, and simulation results demonstrate that proposed estimator outperform as compared to the existing like orthogonal matching pursuit and sparse Bayesian learning in terms of estimation accuracy and spectral efficiency performance, and closely approaching the benchmark Oracle least square. So these are the references. So basically in this presentation I have shown that how in first part I have shown that how the millimeter wave hybrid, what is the need of hybrid MIMO, and how the channel for millimeter wave hybrid MIMO can be estimated. In second part I have shown that if we consider the hardware impairment, then how it becomes challenging to accurately estimate the channel. And in third part I have considered the millimeter wave hybrid MIMO in assistance with intelligent reflecting surface and find the cascaded channel, and how the overall channel can be estimated, and different algorithm that proposed one, ZLMS, VSS ZLMS, and SEFW LMS. So these are the basic adaptive filtering based technique for channel estimation in millimeter wave hybrid MIMO systems. So yeah, this is all about from my sides. Yeah, thank you for your patience for listening, and yeah, you can ask any question if you have inquiry.
Thank you so much, sir, for the informative session. We have received a few questions from the participants, and we will address those questions one by one. Okay, the first question is, what do you think is the most critical barrier preventing large-scale commercial rollout of massive wave MIMO in dense urban environments?
What is the most critical barrier preventing large-scale commercial rollout for massive MIMO?
Massive wave MIMO in dense urban environments.
Basically, one means if we take the massive MIMO, there are basically in terms of large number of array size, and because a large number of array size can be installed in only at the base station side, and no, I think yeah, can you repeat, ma'am, question again?
Yes, sir.
Sorry.
What do you think is the most critical barrier preventing large-scale commercial rollout of massive wave MIMO in dense urban environments?
But there is a rollout, massive MIMO system is already in use. I think this question, barrier may be a channel estimation part, or array means how to beam form, means if there is a dense one thing, that is if there is a dense dense urban scenario, then blockage will be there, because we can apply the large massive MIMO for high frequencies, and if there is more blockage, then there will be more blockage, then we cannot use for a large distance. But for picocell or microcell, we can use this, but not for large range, I think so. So the basic barrier is corresponding to there is a line of sight part, means if we use the very massive very large antenna array size, then there will be sharp and directed beam, and but if there is a hindrance, or there is in urban scenario, there are buildings and other object that we can that due to that there may be hindrance of beam. So I think one thing may be that part, but there may be others. But for a small scenario, there is I think there is no such hindrance corresponding to in urban scenario. Means in femto or picocell we can use this. I think I will be able to clear. Yeah, I hope.
Yeah. Thank you, sir, for that clarification. Next question. How do you foresee machine learning contributing to wave link adaptation and beat management in next generation networks?
How do you? Yeah, machine learning. Yeah, we can apply the machine learning for beamforming purpose. We can also apply the machine learning for channel estimation. As we can see here that channel estimation is most important part of any millimeter wave system or any sub-terahertz or terahertz system. So here, as adaptive filtering, in place of adaptive filtering, we can also use the machine learning to estimate the channel for cascaded part or a different separate part of the systems. So we can also apply in signal processing part, because and signal processing means we can apply the machine learning for beamforming as well as for channel estimation part. Yeah, we can use it, and there are very good results in that part. Means many people in research are applying the machine learning and deep learning in for signal processing of this 5G and 6G communication system.
Okay, thank you, sir, for explaining. So next question is, what is the single most restrictive hardware imposed constraint on the analog RF precoder that significantly complicates the signal processing design? And how does this constraint force the use of advanced optimization algorithms?
1 second.
Do I need to repeat, sir?
Yeah.
Yeah.
One thing it is written. Single most restrictive hardware imposed constraint
on the analog.
Good question. And I think in analog RF precoder, if we used only analog RF precoder, then there is only one RF chain for each antenna, and if we use only one RF chain in analog precoder, then we cannot find the multiplexing gain. So if we use only RF precoder, then we cannot find the multiplexing gain, only because there is only one RF chain that is connected to all the antenna. So this is a basic thing that I think this is a basic restriction that we go for the hybrid precoders, means RF and baseband precoders, because we have to with the help of hybrid precoder, we can simultaneously find the multiplexing gain as well as beamforming gain. But with use of only analog precoder, we can find only beamforming gain, but not multiplexing gain. So, and yeah, that is a basic thing that that restrict the main constant for use only RF precoder in higher frequency range. Yeah, I think so.
Okay, thank you, sir. The next question. Could you please explain how the L1 norm penalty helps in enforcing sparsity in adaptive filter coefficients?
Yeah, good question. So, basically here I can so is it visible? Because my slides are visible.
Yes, yes, sir. Yes, sir.
Yeah, okay, great. So here we can see it that yeah. So here we can see that basically the channel estimation problem is given by this equation 28, and here, because actually what happens when we estimate the channel, then our aim is to find the non-zero part, or we can say non-zero element of the channel. As I have already told that millimeter wave channel or sub-terahertz channel are sparse in nature. because there are less number of paths as compared to number of transmit and receive antenna. So if we apply here we can see that if we apply this penalty term, that is this penalty term means gamma FHBN, then what the function of this one, that if we apply the L1 norm, then the overall update equation is given by overall update equation. I think 1 second. Here I have write the overall update equation for ZLMS. Yes, here the overall update equation is given by this term rho SGN HAN, and as you know that the signum function that is given by x upon mod x, so it is either 1 or minus 1. So it is 1 no SGN function. If we find the SGN function, as all of you know, then what happens, then it will make the element close to the 0 if they are very small. Means if they are small, then this function make them 0, means it increases the sparsity, this, and it attract the sparsity due to this function, SGN function. And so on the basis of the multiplication of rho, that is a regularization pattern, and the value of this also attract the sparsity, and the product of these two terms will overall define the sparsity. Means if the element of this vector is close to the 0, then this part make them 0, and overall sparsity will increases, and hence this 0 attractor term increase the convergence rate of the overall algorithm. Yeah, I think is it clear? It will be clear.
Yes, sir, that was very insightful. Thank you, sir. So we have addressed all the questions for the time being. So we hereby conclude today's session. So from the organizing team, I sincerely thank Dr. Vidya Bhaskar Shukla for taking today's insightful and enriching session. On behalf of the ATAL FDP organizing team, we truly appreciate your valuable time and knowledge you have shared with us today. Dear participants, okay, sir. Okay, sir. Dear participants, attendants, and the fee. Yes, ma'am.
Yeah. So I also really wanted to wholeheartedly thank you from the complete ATAL FDP organizing team for such a wonderful and inspiring session, and especially for graciously accepting our request for the session, sir. It really means a lot to us, sir.
Thanks.
And we really appreciate the time and effort. Yes, sir. We really appreciate the time and effort you took to share your knowledge with us. Thank you once again from our complete team, sir.
To all participants, and yeah, they listen patiently, and also they engaged in overall session. I think I have give some insights and some research direction for future. Yeah, thanks a lot.
Yes, sir. Yes, sir. Thank you, sir. Yeah, you can continue.
Okay, ma'am. Yes, ma'am. Dear participants, the attendance and the feedback form has been shared in the WhatsApp group as well as in the chat box. So please make sure to fill and submit it by today. With this, we conclude today's session. So please join us again tomorrow at 5:30 p.m. for the next set of sessions. Thank you all and have a pleasant evening. Thank you.
Okay, thank you. Bye-bye. Good night to all.
Thank you, sir.
Thank you, sir.